you all are going to drive that horse, and I'm telling you right now, because I got a feeling nobody's asked for it in years. They ain't going to put it on there.
Not AP biology in the
It's always been on there. That's the class that just kept going. So that's the one that we're supposed to offer an AP class in every criteria, every subject. So math, science, social studies, every field's supposed to have an AP class. That qualifies AP biology.
So there should be an AP Contemporary Studies.
Yeah, there's no AP Trig though. AP Trig is calculus.
But Trig is online.
But this is my thing is, you guys are going to have to drive that horse. That you're going to have to sit in there when they start talking about your science classes and what's offered. You're going to have to raise your hand. You're going to have to go, what about AP Chemistry? A lot of us want AP Chemistry. And I know a lot of people are terrified because they think that you go from a regular class and you go to AP, we kick it up a notch. I'm going to be completely honest with y'all. What you get, what you get. I already drive this class like it's AP. So you're already going to be used to it. The only difference is going to be, I've already brought you up and got you used to a science level AP class.
Yeah, I literally was looking at the AP exam practice test for chemistry, and like the first few questions, like at the beginning has a bunch of formulas. Every one of them, there's like 2 or 3 on there that we haven't went over yet.
I'm not taking no electric.
There's stuff on that y'all could pass right now.
AP Chemistry.
But there's just a lot more stuff that we have to cover in order for you to learn it so that you can do it. And then we also have to have enough time before it to give you the practice exam so you guys can see it and you're used to it.
Class me to get like a 5 on the AP Chemistry exam. No, you have to take it.
All right. So today is one of my favorite days. I love getting to this day in chemistry. This is going to be fun.
Are you sure it's going to be fun?
Is it lots of artwork that we can be about?
Just one noble gas.
So everything we're going to do today is going to look at one central idea. And you've already been exposed to it, so don't worry too much. It all looks at wave-particle duality. All wave-particle duality is, write this down to the vocab stuff, must have defined. Wave-particle duality is how something can be a wave and a particle. So this brings us into a very interesting experiment. One that you've already seen, heard of before. I told you it would come back. What did the double slit experiment do? It proves light to be a wave. How does it prove light to be a wave? Interference pattern. So all of you that thought on that quiz were like, that's a repeat question. We've already had it. And I told you it served a purpose. This is the purpose it serves. I wanted it fresh in your mind because of what it did. I'm going to do some erasing and stuff. So don't get too carried away with copying stuff down right now. So we started with a light source, right? Then there was this wall, for example, and then in the wall we had 2 slits, right? And we did this so that the only thing was the light would radiate out would come only through the two slits. So then what happened here at the two slits? It radiated out from that point to where we see on the back wall this interference pattern, correct? This is not the part that messes with your brain. This is review. You say, yes, sir, here. Okay, cool.
C.
So, what did the double slit experiment prove? Light to be a wave, interference pattern. So then we get into the world of, well, why not? Someone had just a great idea one day. Said, you know what, let's change it. Let's no longer do light, just for the fun of it. Because I said today's going to be fun, right? They changed this. Same experiment, same setup, but something's different. We no longer use light.
Bowling ball.
Sure. Really small bowling balls.
Particle.
Also known as
What did you just say though?
I don't know. It just wasn't in my head.
electrons.
Oh, I wrote down a lot.
So this is where this is going to mess with your head a little bit today, okay? But this is where you got to drop your pride at the door. You got to ask questions. This, what I'm going to explain to you today, should mess with you a little bit. I'm just being honest with you. That's okay. So scientists had this idea. Well, hot diggity dog. Let's do it with electrons. So they set the whole experiment up. They set an electron emitting source up, which just emits out electrons. Now, what is an electron? Negatively charged subatomic particle. In this case, the subatomic particle is the one we're focusing on. So it's a particle. Don't get too carried away, though.
You missed yesterday. You don't even know what we did.
Subatomic particle. What should we see on the back wall?
Subatomic particles.
It's a particle, right? What we see.
You think it'd just go straight through?
So it goes straight through. So would we see two bands?
I mean, you'd think so.
Okay. So scientists did this, and here's the cool thing. So this is what they got.
Three, four. Well, that's fine.
I didn't make a mistake. So here's the cool thing. The electrons were firing through. Here's the freaky thing. It's exactly what you think. It's exactly what you said. What should you see? Two bands. Why? What's an electron? Electron's a particle. So I should have two bands. And then scientists go, whoa! How do we get an interference pattern? We've done experimentations. We know that this is a particle. What is going on? Oh, wait a minute, wait a minute. I know what it is.
So where's the particle?
My electron emitting source. It's just shooting out too fast. It's shooting out a bunch of electrons. So let's say, let's alter the experiment. So, they altered it. I told you I can do a lot of raising. So they alter the experiment. Set everything back up. They said, now, let's set this up where only one electron at a time is going to go through. So it's like one electron goes, a couple seconds, an electron goes, a couple seconds. Why do this? The reason they're doing this is because I feel like I have one of my wife's hairs stuck to me. There it is. Mary, she goes everywhere with me. How my wife has hair in her head, I do not know. One electron, wait a little bit, electron, wait a little bit, electron, wait a little bit, electron. So it's like, now, not all these electrons firing off interfering with each other, because what are electrons? So, negatively charged subatomic particles, so that negative charge can make them repel off. Fix it, no problem, right? We're good. It's great. So they did this. And they get a pattern.
Ain't that the same thing?
But slightly to the right.
Thanks.
Trying to help you out so you can explain this.
What is this? Interference pattern. So they changed everything now. Only one electron's going through at a time. And they still get an interference pattern. Now, what's an interference pattern a characteristic of? A wave. So they're sitting there and they're freaking out. Hold up! Stop the presses! What in the world? This makes no sense. It's a particle. And it gives me an interference pattern, which is characteristic of waves. It don't make any sense. So then scientists get smarter. And they're like, I'm going to figure this out. I am smarter than it. They thought. Said, here we go.
But Mr. Hall, whenever he sees it, I'm smarter than you.
No, it was a donut.
Yeah. Yeah, because we got some donuts, so
It's like when Miss Hall brought me those Oreos. You throw it back at her, I'm smarter than that.
I've been scared. She would have probably used at my head. You would accept the Oreo. All right, interference pattern. Characteristic of wave. Scientists got smart. So they're like, okay, something's going on. They're going one at a time. How is this even possible? I mean, it's one electron at a time. It's either you go through the slit or you don't. That's it. There's no, hey, let's go through here, let's do a loop-de-loop and pull. No. It's you go right through the slit.
It went over and back.
it's like a phone booth.
So then, scientists decided, let's just set a device here and let's figure it out. We got to figure out what's happening here. Let's set a device. So they set a device. The device's job was to measure and observe which slit the electron went through. So now we've set it up and we're observing. So now we're watching the electron. So now, you know, the electron's sitting there. Always feel like somebody's watching me. So then, here's the really cool thing. You ready for this?
No.
I told you today's going to be fun. So they set the device.
But there's even more now.
Oh, hold on. I told you I was going to raise
I
it.
bet bounce off on the corn now. Bounce it off of the line.
You ready for it?
No.
That's me. If I was there, I'd say for all.
This is a redraw.
Done. How does that make you feel?
It was like too many tornadoes.
Is this so
So, the whole time we've been getting what from the electron? What type of pattern on the back wall? Interference pattern, which is characteristic of a wave. And now all of a sudden, I put something there to observe it, And the stupid little electron goes back to acting like a what? A particle.
It's bouncing off. It has to be. It's bouncing off that.
So then they start looking and saying, we've messed something up. Something's happened. We've messed something up. Something's went wrong. We've jacked something up. Let's clear house. Let's repeat the experiment. Every time they did this, this kept taking place. And it kept happening. So there's only one conclusion to come to.
We don't know.
Oh no, we know.
You know.
It's a gamma ray.
Not only is light a wave and a particle,
So I was right the first day.
the double slit experiment shows and proves electrons are wave and particle. This is the part that gets freaky and weird. How can something that is a particle be a wave? But then how can something that's a wave be a particle? Made sense of photoelectric effect because photons. Photons just a small little
Particle with no.
amount of energy. Small little packets of energy. It has a certain quantity of energy but no mass. So it makes sense. There's no mass there, so you're not going to have the particle there. But then all of a sudden we know the electron, we know the mass of an electron. There's mass there, but all of a sudden we have a subatomic particle acting like a wave and acting like a particle. And then it gets really freaky because if I start observing it, then it's like, oh, I got to be a particle. But if I leave it alone, it's like, I'm a wave. I step in, it's like, oh, I'm a particle.
It's like a.
If I'm a wave.
When he would put his hand out, the whole crowd would cheer, but we take it back there. We only use SpongeBob for
This is the thing that has opened up the world to what we have today. This right here is the basis and the background for everything quantum. Quantum mechanics, quantum everything. Everything revolves around this premise and idea of one thing. The electron is a wave and it's a particle. Here's the freaky thing. Let's say Dalton is doing an experiment and he needs the electron to be a particle. What's he got to do?
Nobody could ever.
Absolutely nothing. Just say it's a particle. Well, what did you do to make sure it's a particle? I did nothing. It's just a particle. Guess what the electron does? You didn't mess with nothing. It acts as a particle. So Brady goes. Brady needs the electron to be a wave in his experiment. What's Brady need to do? Absolutely nothing. You know why? It'll act as a wave. The electron has wave-particle duality and it'll act however you need it to act. So this is the idea that scientists came up with. How can electrons be waves?
Good day to have allergies.
There you are. Okay. How can the electron be a wave? So this is the way that scientists looked at it. If electrons were waves, that within those waves were trapped around the nucleus. Then what would happen is they could only have the setting. I won't say it. They could only feel / be in certain energy levels. So the electrons as waves, and the idea is if the electrons were waves trapped around the nucleus, then they could feel and be in certain energy levels, which you learn your energy levels, which opens the world of possibilities to us. There's other experiments that's been done to prove this. But the really freaky thing, you guys have probably heard of this before. All we've got to look up, make sure I spell this guy's name right. Let's see what time we do. Oh yeah, we're going to get them both in today. This will be great. Say you've heard of this guy before. There's a very famous thought experiment that he has dealing around this. He's German, so I gotta make sure I'm spelling his name right.
Germans and their crazy names.
Schrodinger's cat. Should sound very familiar.
It does not.
Never heard him.
You guys haven't heard
Schrodinger is, Erwin Schrodinger, is a German scientist, that he came up with a wave equation explaining this phenomenon. Because here's the weird thing. I should have explained it better.
Is that a real cat?
No.
Meow.
In the double slit experiment, this ain't a part of Schrodinger's. It is part of Schrodinger's cat, but not a part of Schrodinger's cat. I should have explained this a lot better. Whenever this is going on, mathematically, to get this interference pattern, and this is when you have mathematicians, physicists, everybody's coming on the scene, everybody's jumping in, everybody's like, this makes no sense. This is the interesting thing, is whenever they did the one electron at a time, it didn't matter. They did a mathematical calculation of it. And this is what they mapped out mathematically. The math is even weirder than what's actually happening. So this is what the math says. The math says that electron hits the wall. It also says it goes through the left slit. It also says it goes through the right slit. It says it goes through both slits. It says it goes through no slits. It says it's over here in the left corner. It says it's back here on the wall. It says it decides that it's just going to fill the whole thing. Well, it's over here now. Mathematically, the electron is in a wave of potentials to where it's in all sorts of places. Even when you're sending one electron at a time, the electron will just flow through one slit, but the other slit at the same time. It'll come through the left slit and the right slit and interfere with itself on the right slit and the left slit. And it comes back on the other side. If this is bothering you and freaking your mind out, I understand. I'm the guy that's teaching this and it freaks me out. this is the thing. Mathematically, it gets so interesting. And this is why we have the invention of the thought experiment that Erwin Schrodinger came up with. And if you're being bothered by this is freaking you out, and you're like, do I know anything?
But wait, there's more.
An electron's a particle. He says it's a wave. Now he says it's both. What in the world? Erwin Schrodinger helped develop this idea, the basis for it, and it freaked him out. You know how he ended his career?
Suicide.
Millions.
Being a botanist, he decided to go study plants.
Did you say suicide too?
Oh, we're all.
I mean, we all thought it, but we weren't gonna play it. Not really.
You know, I said we'll say it.
I said, end his career, not his life.
I honestly thought you were about to say, okay,
Yeah,
they
but
chose
that's take
you
your
for
career
your
blame
job.
too. I mean,
Need
you
someone to
can't
jump
career
down. Alright.
blame.
Listen, if I spent
That's
my
an
life
everything in there.
an electron, I would just.
So here's the thing, before anybody looks at me, wait, hold on, I gotta make sure and do something so I don't get canceled. This is just a thought experiment. This really did not happen.
We're not condone bad behavior.
Okay, anyway. So before anybody freaks out and they're like, oh my God, he's gonna kill a cat. It's a thought experiment, people. That means you're thinking about it. You really didn't do it. It's just trying to take something that's happening on the quantum world and bring it to our level, to where we can understand what's happening. So Schrodinger's cat is all based on this idea.
It's a hypothetical. Basically.
We have a box.
Should we?
Huh?
Should we draw on that?
It's a box cat though.
Sure.
Experiment.
Cat.
In the box, we have a cat.
Yeah.
No, I have to use double
We're gonna put some squid things up in here.
Oh, man. You going all out on this
Let's
cat.
tell FP that Mr. Hawks over tonight class.
We'll tell you big one of
You're here now, Miss Adams gonna come down and like, what are you doing in your room?
And it's like, you have a cat like slaving on the table 1 second. Oh my God.
What are you doing, Mr.
That
Hawks?
looks like a person. Please put ears on
It
it.
looks like a bowling cat.
I just put the word cat.
Oh my.
Is that antlers?
Alright, guys, quit being mean.
This wall,
Please
you just
put
put ears on it.
Mr. Hall. It won't look like a little boy.
Hey,
There you go. Now it looks like.
now it looks normal. Now it looks
Alright, so here's my cat. Poorly drawn as I can possibly
It looks
be.
like a corgi, but in cat form. Or a cat in
The
the
word
word
cat.
form.
So here's the cat. Now here's the interesting thing, and you get different explanations of this thought experiment and this idea. You get a whole bunch of different ones. So here's the big one. So we got the cat. The cat's in the box. Also within the box is based off the premise of this. I'm going to go very simplistic because I'm not very artistic, so we're going to stay very simple.
Oh, I do hard stuff. Like human awesome.
Along with the cat,
Loves the cat.
Oh, well that sounds really nice.
we put a bomb.
Oh.
Hope that poor cat's gonna go bye-bye.
Remember, this is a thought experiment. Don't cancel me, YouTube.
I know what my singing prank's gonna be.
Oh.
We're just gonna put it right
You wanna-
here in this hallway and
Just,
put a
no,
sticker
just
on
put
it.
it in front of your door that says cat inside.
I would die. I would
Done
die.
by Mr. Hall.
Let you,
I would literally video that and put it on TikTok.
I'll let you figure out the rest.
Yeah, I'll leave a sticky note on the office. That experiment was conducted by Mr. Hall.
Yeah, thanks so much.
You
All right, so here's the thing with the bomb. The bomb has a 50% chance of exploding and a 50% chance of not. So it's 50-50. So here's an interesting thing. I put my cat in the box. I put the bomb in the box.
Yeah, not a lot. You're good.
I set it on Taylor's desk. And I asked this question to you. Is the cat alive or is it dead?
It's alive.
It's alive.
It could be either or.
Well, I mean,
You don't know?
well, if there's no holes
Here's
in
the
the box,
thing.
then it's not alive.
That comes out of this, and this is why the thought experiments become very popular.
You gotta think outside the box. There's no air in the box.
The cat?
You said think outside the box. Well, actually, we have to think in the box. Or was I right?
Cat is alive and dead.
Oh, because it has a bunch of radioactive isotopes in it.
The cat is alive.
The cat is dead.
But it's dead.
The cat is dead.
That's your awesome.
Long live the cat.
Oh, he didn't live very long if he's already dead.
The reason behind this, because we don't know.
He's lactose intolerant.
Exactly what you're saying, Austin. This is the thing. What this is what is explained in quantum physics. And this is what Schrodinger's cat thought experiment is all about. A superposition state. Superposition states is, it's various, this is the way to look at it, it's multiple positions. Position 1, the cat's alive. Why? Because it's a feline, we don't want it to die, even though my dog almost killed one.
He is actually Adolf Schrodinger. I don't remember his first
Cat,
name.
Erwin. Cat is dead. Here's the interesting thing. The cat's alive and dead. Here's the thing. This is what's happening with the electron in the double slit experiment. The electron goes through the left slit. The electron goes through the right slit. The electron goes through both slits. The electron goes through neither. It goes through one and interferes with itself on the other. It's in a state of superposition. So when it's going through, all this is happening at once. But whenever we put the piece of equipment there to measure which slit the electron went through, what happened? It goes back to being a particle. You know why? Because we collapsed the superposition state. I then know where the electron was. It's the same thing as my cat that's in my box that I just set on the desk and I asked you, is it dead or alive? You know with 100% assurance. Mentally, it has to be alive or dead. But until you open the box, you have to tell me, which is it? Well, it's alive, it's dead, and it's both. It's in a state of superposition. Because what's all the possibilities? That's what you're looking at with this. This is what brings us into the whole freaky part of what we're talking about and getting into. So how do you answer the question? Is the cat alive or dead? You open the box. Once you open up the box,
You get attacked by a cat.
you then know, because of observation, you look in and you see if the cat is moving or attacks you. If the cat attacked me, don't worry, the cat won't be alive much longer.
I want to say don't cancel me. I'm going to say don't cancel me, YouTube.
You'll get Trevor. Well, he's dead, so I don't know how it died. I don't know what I thought it was fine.
Mr. Hall opens the box, comes out, my shirt's red, bloody mess. It's like, oh, the cat's alive. No, it's dead. That thing was not a house cat. That was a stinking tiger. Okay, I fought for my life.
The bomb accidentally.
Here's the thing. This is what I want you to get before you walk out of here. Give me a second. Focus with me. This is a conceptual thing. You have to be able to explain things. It's in superposition state until you open the box. Once we open the box, that's when you know it's either alive or it's dead. It's no longer in the superposition state. You know. This is what was happening in the double slit experiment. Whenever we put the device to measure where the electron was and where it was going, as soon as we did that, what takes place? We collapse the superposition state. I'm going to stop here today. How many of you feel like I have messed with your brain and you are fried today?
I don't even, you talk about stuff, but I don't know what cohesive
This is how my brain works.
Like, I don't know what to grab.
Listen, this is the thing. Tomorrow, don't miss tomorrow.
Can I please get a waffle?
I'm coming in tomorrow.
Listen, tomorrow, I'm continuing on with this. Okay? When I continue on with this, we're going to discuss quantum entanglement, Heisenberg's uncertainty principle. For all those in the room that want to know, that is where they got Walter White's name for the show. Don't mention the show. I hate the show. I despise it. I wish I could burn every episode.
I don't even know what it is, so we're doing good.
Put the hoodie off, and I'll turn the corner and put it back on.
He's got that.
You saw it right where he said something, didn't you? He said,
Your door accidentally shut too quick.
So the negatively charged subatomic particle, but it also is a wave of potentials. So we look at them as a wave of potentials that's trapped around the nucleus. In this case, they can only feel certain energy levels, which we know that they do. Now, the interesting part is, they prove this with what experiment?
A double slit.
How did the double slit experiment prove it? The interference pattern. Now, what's the really freaky thing with electrons in the double slit experiment?
when you stick something in there to try to catch it, it acts different.
You know, when you stick a device in there to measure and observe it,
It goes back to acting like
a
particle. Why? Because before you put a device in there, the electron is in a state of what? Superposition, which is it's a wave of potentials and probability of being in a vast majority of areas. So without the device here, the one electron is here. It's here, it's here, it's here, it's there and here. It's here but interfering there. It's there, it's up here. It's not even here, it's in a totally different room. It's all over the map. The mathematical probability of the electron is the fascinating thing. As soon as you put the measuring device there, what happens?
yeah, acts as a particle.
Acts as a particle, but why? What did we do? We collapsed the superposition state. When we collapse that superposition state, it's the equivalent of the Schrodinger's cat thought experiment. You like that cat?
Well,
Yeah.
Very nice, right?
Why does it look like a ring? It looks like a ring.
Because it has
bro, that'd be
on
dope,
its
right?
belly.
I don't know how to tell
Lord,
what
Dalton. So mean.
I'm not mean, I give constructive criticism.
Oh,
It's okay, I was muted yesterday, so I can laugh as hard as I wanted to.
I should just hung up. Okay, so cat's in the box, bomb 50% going off, 50% not going off. Close the lid. Is the cat alive or dead?
It's alive, dead, and alive, dead.
It's alive, it's dead, it's alive, dead. It's in a state of superposition against all these probabilities. That's the way to look at it. The box is closed. State of superposition. It's in all probabilities. You have to accept the fact that the cat is in all situations. That's what we're saying with the electron. The cat's the electron. It's in all probabilities of where it can be. Now, we open the lid. You can tell a couple of things. First, we can tell if the cat's alive or we can tell it's dead. 100%. So if we open the box and the cat's moving around and it's meowing, the cat is alive. If I open the box and the cat jumps out and claws my face, the cat is
Almost dead.
it's dead. I'm going to tell you that right now, because when I'm finished with it, it'll be dead. It'll jack my face up. It's a joke, YouTube. Don't cancel me. This is the whole idea with the thought experiment here. So, I now get to get you into one of the very interesting ideas that have led from this. So, after all the work that went on, there's multiple men that kept adding to this. So we find ourselves taking a trip with another scientist.
Wait, real quick, what's superposition again? I did not have that down.
Superposition. Trying to find a way to define it where it makes sense. You know how I am. I don't want to give you like a Google definition. I want to give you a definition that makes sense.
Can be, superposition means it can be in any place into.
So basically the electron is like anywhere and everywhere unless proven.
Yeah, pretty much. That's really the way I look at it. Alright, so superposition is the state that the electron, I'm saying electron because that's what we're focusing in on, but this could be like the vast majority of various different things. So those of you brilliant minds of America that's going to go on and change the world as we know it, that you will go to college, you will become the greatest scientist or physicist ever, and you will be so inspired from your chemistry and physics teacher, when you take physics next year, that you will come back and donate $1 million to let him buy anything he wants for the school.
I thought you wanted us to try to get AP chemistry.
I want AP chemistry. Yes, absolutely.
I'll donate $1 million and tell you you can only use it on books.
Oh, $1 million book grant for the man who doesn't use books.
Okay.
No, he's thinking now he's gonna do something with the hot name book.
Don't worry, I got plenty of time before I get the $1 million to come up with how I can turn books into what I want.
You buy the books, you sell the books back, you take the money, and then you buy what you want.
No, you buy the books out of a secret vendor that actually cut a hole in it and put something else in it.
That's called illegal.
Very illegal.
I call up the company and order stuff from, hey, can you put on the inventory that these are books? So superposition is the state that the electron is in all possible states at one time. So it's all about position, where the electron is, and superposition. So it's on all of them at the same time. 8th period came up with the idea of ultraposition. I said, no, we're not doing that. So, I'm going to address this. I want everybody in the room to know one thing. I despise and hate that show. Do not mention the show in this room. Do not ask me the question. I've made it this year so far without being asked the stupid question. Don't do it.
I don't even know what show you're talking
I'm
about.
going to answer, if you have watched the show, this is where his name came from. Today we're going to talk about
Someone please tell me the show.
You'll know once you see it, no problem.
You don't have what it's from.
Oh, they have no clue what y'all talking about.
He talked about it yesterday. Google it, Dalton.
talk to you about the Heisenberg uncertainty principle. Dalton, I will break my rule. I will address the show just so that you know. It's an awful show, absolutely horrible. Just don't watch it. Breaking Bad.
Oh, that's so dumb.
You don't like that show?
I've heard of it. Just
I've
never
never
watched
even
it.
seen it, and I don't even plan on.
Despise it. Ever since that show came out and I was in college,
But it's about math.
every education class we get into, it'd be like, introduce yourself and what you're going to teach. And I'd come up and it'd be like, Hey, my name's Kevin Hall. I'm from Southern West Virginia, and I'm going to teach chemistry. And they go, Breaking Bad. Had a guy one time, I seriously, and y'all know me, I love the Lord, and the Lord's still working on me. I wanted to break the guy's jaw. God just wouldn't let it go. And he even did the whole Oxyana thing, and I was like, I looked him straight in the face, and I said, dude, you just need to shut your face right now. All I got to say, you better shut up. With a professor in the room, I did not care at this point. Okay. Heisenberg uncertainty principle.
I still don't understand how this goes with that show. I really don't. I never watched the show either.
In the show, for his code name, it's like Walter White, right?
Yeah.
Walter White is a chemistry teacher. But then the guy that's making math and selling it and becomes like the dude at making the math, selling it. His name is Heisenberg. This is where it came from.
Well, I think I've heard of that now.
At least you use like some smart terms. Instead of something like pork chop.
There you go. You know your buddy chopped down the road.
Which again,
Alright, here's the thing that Heisenberg's uncertainty principle states. Now this works for the quantum world, the quantum realm, so subatomic. But the Heisenberg uncertainty principle states it is impossible. We cannot. It's impossible to determine. It's impossible to determine the velocity. You guys probably have never heard of velocity before. For those of you that are going to take physics next year, you'll get so much joy with velocity.
I've heard of it.
The agility. The
That means
velocity.
don't take physics?
No, that means take it.
No.
Velocity is not really a big deal.
All velocity is, it's the physics term for speed.
If anyone's ever watched The Flash, they know velocity.
That's true.
The velocity.
So determine the velocity, which is just the speed,
I don't care.
and location.
oh. What's this principle called again?
Heisenberg uncertainty principle.
On the board.
Did I misspell it?
Yeah.
Insanity.
Uncertainty.
I don't even care right now. I'm so tired. Don't even care. Make it right in your notes. The fact that I gotta be honest with you, I sit here and I'm staring at speed, and I'm like, I don't feel like this is right. I don't even care if it's wrong right now.
It's probably like the law to make like
Insanity.
the law to make like.
I can't tell along the road.
I don't even care. I'm like, seriously. I'm like running off 3 hours of sleep and I haven't even made it through a full cup of coffee. I'm here though.
Uncertainty is good for me.
That's what we're gonna write on our test.
Oh, God help me.
I spelled it wrong.
And location of the electron at the same time.
You know how to spell it either.
No, keep it like that. Sort of.
There you go.
I don't know why I was preaching. I spelled it wrong on my paper too. I'm sorry.
It's okay. What I said, I meant, I'm so tired, I really don't care.
Okay.
So the electron at the same time, by measuring one, we change the other. So here's the thing. It's kind of like, to get you an idea behind it, is bringing us into, taking this idea and bringing it into modern, like, real life, not in subatomic, but bringing it into macro world, us. So let's say I have a helicopter. Mr. Hall is like, tomorrow morning I'll bring you all in Krispy Kreme. It'll be hot and ready, because, you know, as early as we get up, the donuts will be hot and ready in Charleston.
That would be a macro deal.
It's like Little Caesars.
So,
donuts.
let's say I'm flying my helicopter and you call me. And it's like,
All the time.
Mr. Hall, where are you at? And I look at you and I tell you, I'm at mile marker 37. When I tell you I'm at mile marker 37, I'm driving through, well, I'm flying through, I see mile marker 37, and then I say, I'm at mile marker 37. Am I there anymore?
No.
No, why? Because I'm moving.
Yeah, so if you don't pass it up, you're probably down
Yeah.
mile marker 36 by now.
I'm no longer in that area. It's kind of like, let's take the room, turn off all the lights, and I'll set a random bowling ball somewhere in this room that's moving around on a frictionless surface. So anybody watching this that knows physics, it will keep moving. So your job and your task,
Motion says it won't.
oh,
It's not, it's
It's
just get rid of
friction, so it
friction,
will
that's
keep
the
going.
force.
So
Come on,
I know
all the
about
same.
the laws of motion.
that's okay. I'll see you in physics next year. I get to physics. And in physics, I get to friction. And in friction, kids cry. And I'm like, it's so easy. Why you cry?
It's just hot.
No hot.
That should be our electric ride.
It is.
Turn off the lights, you know?
And roll the
Taking a
ball.
nap, great idea.
Taking
No.
a We'll take it
So,
and roll
bowling
the
ball sitting in here moving. Your job and task is I want you to tell me the velocity, and I want you to tell me the position. Would you be able to do it? No. But, let's say you wanted one or the other. So the way that you can do it is taking bowling balls, yeeting them through the room, until it collides with the other bowling ball. So once it collides with the other bowling ball, you hear the noise. So at that moment, you know where it's located, right? But then the bowling ball that you yeeted at it comes back at you, and you measure that bowling ball's velocity coming back at you. You do some calculations, you work it backwards, and you find out, hey, this is how fast the bowling ball is traveling. Is the bowling ball still in the same location? No. For us measuring one, we change the other. This is the thing with the subatomic and quantum realm. Heisenberg's uncertainty principle gets us into this idea that you cannot know both. You can only know one or the other. And the really freaky thing is, it's a probability of either one of them. Which brings me to one of my favorite things. This is something I took on when I was student teaching, and the teacher, my supervising teacher said, we don't teach that here. And I was like, what? He said, yeah, it's so complex and complicated that we just decided not to even cover it
Thanks, Mr. Hall.
because it takes so long and it's hard for the kids to understand.
Well, I think it's awful to deprive great children of their capabilities.
Yeah. I think it's awful that they don't make children be stressed.
Exactly, right? It's good for a kid to cry every once in a while.
It is. Good girls do cry.
Oh, holy smokes, my wife's gonna kill me.
Did you not
I did not tell her I was here, and I just felt my phone vibrate.
Oh. Tell her you stop for donuts in Charleston.
in a helicopter?
And you're at mile marker 87.
Yeah, so
But you're
Mr.
figuring it
Hall would
She'll be
be
so confused. She
very
doesn't know.
much enjoyed.
And then every like 2 seconds you say 86. 85. 84. 83.
think she's used to me forgetting. All right, so the 4 quantum numbers. These 4 quantum numbers, you know how we did those electron configurations? And I looked at you and I told you, just accept it. This is the part I was saying, just accept it. But it's going to make more sense there. The other thing that comes with this is we have 2 types of problems, well, 3 types of problems we can work. And guess what? Know the pattern, find the answer. There's no trick. Know the pattern, find the answer. It's that simple. Everybody got it? So, the first one.
Number 1.
First one should be very familiar to you. This is the principal quantum number. I know what you're thinking. I never heard of this before till you, Mr. Hall. What is the principal quantum number? Principal quantum number has an abbreviation. Once you see the abbreviation, you will know what we're talking about. Principal quantum hashtag. Principal quantum number is abbreviated.
Sine squared plus cosine squared is 1.
Say trick.
Oh, that's crazy because like n equals this crazy.
Is equal to n.
You know, like the
Like every
row
question,
minus 1, that thing.
n equals blank.
Now I'm still don't know where it's coming from.
So this is what the principal quantum number tells us.
He just did these all.
I hope not. That is so
You know, on the periodic table, when it was like your block is your n minus. Oh yeah, you did.
Oh, I know I did.
All right, principal quantum number tells us a couple of things, and I'm going to work a couple things in. First thing it tells us is the energy level. Other thing it will tell us besides the energy level no, that's what it tells us. This is what it shows. That's how I did that year. So it tells us the energy level. This shows us rho on the periodic table. I think you guys remember it pretty well. So remember, you got, oh, I don't want to do that color. What am I doing? You got S, P, D, and F. For S, N is equal to the rho. This also states that rho is equal to N.
Associated.
For P, yes, look at you. We thought you were behind. You're right with us. N equals rho for P, which means the rho is equal to N. For D, N equals rho minus 1. He was number 1. It was his hat, Mr. Krabs. Now, here's the change. I gave this to you this way for a reason. There's going to be a change here. If you need to work backwards and find the rho, let's do some algebra.
Add 1 to both sides. Oh my goodness. N plus 1.
Let's do it. What would rho be equal to?
N plus 1.
Oh my gosh, the ACT and SAT is not ready for your math skills. You would destroy them. Destroy them all.
I took the SAT. I had no school back yet.
You'll destroy it.
You take
I
hot, you take hot SAT or PSAT?
Hot.
Oh, I
Hot ACT.
Aye.
On a Saturday. I wasted my Saturday for an ACT. And they don't give me score.
Oh, you say ACT. I think
ACT.
it's
ACT. A. ACT.
It's too early for this.
No, it's not. It's perfect. It's exactly how they did this morning. The Lord knew. He's like, I have to give Kevin first period chemistry to get him going.
Grande test. Grande test.
F gloss. N equals rho minus 2.
I'm glad they do it, because I don't have that energy.
Remember looking door outside.
I kind of feed off everybody else.
Listen, I believe in you. Your math skills is like here. You will destroy this.
Mine are down here. That's why I'm failing.
You stop.
Rho equals n plus 2.
Oh my gosh. Who would have known that the rho would be equal to n plus 2?
So you would have made it up.
You have to use context clues. See, working across the curriculum.
Wow, look at you. Yeah, there we go. Mark it.
Mr. Hall, I got one question.
Yeah,
You turned in your little vocab yet?
absolutely. Absolutely I did. Miss Hall came by and asked me, and I said, I'll email that to you right now, man. How you know it?
Ran out of time.
What'd you
That's
say?
not-
You're saying you can just write on the board and we write it down?
I said that I define it in simplistic terms and on a level that students will understand
And comprehend.
every time I introduce new terminology into the class. Like superposition.
Aren't you good?
So, this will show us on the row of the periodic table. Now, here's the thing. This is going to tell you and help you out. This is the first type of problems you can work with. They have possible ranges. So, the range for the principal quantum number. N
Probably.
can be 1 to 7. The key to this must be a whole number, and it cannot exceed 1 through 7. In other words, it could be 1, 2, 3, 4, 5, 6, or 7. That should sound familiar to you, because how many rows are on the periodic table? Wow! Look at the conclusions we are drawing, the relationships between what we have learned.
Because that's like the most electrons you have too. That's crazy, almost crazy, really. It's like part of your
What
electrons.
did you do? Alright,